Our goal in this series of videos is to find the solutions to Legendre's differential equation. And in the first video, we used the power series solution method to find the recurrence relation. And this will be helpful to find the solution to Legendre's equation. What we will be doing in this video is write down the form of this solution and analyze the radius of convergence of our power series solution. One thing to note about this recurrence relation is that it relates n plus 2 with n. And therefore, we got to consider the solutions where n is odd and where n is even in order to fill the entire set of natural numbers. Because imagine if we only had C naught. If we only knew C naught, well then we could know C2 through the recurrence relation, and then C4, and then so on. But we will only know the even terms. Therefore, we also have to consider C1 in order to fill out the odd terms. And so if we consider C0 and C1, we can fill the even and odd numbers and therefore the whole set of natural numbers. For example, using the recurrence relation, we find the expression of C2 as a function of C0, which is 0 times 1, so 0, minus k, over 0 plus 2, so 2 times 1, minus k over 2, C0. And similarly, C4 is equal to, this time n is equal to 2, so 2 times 3, 6, minus k, divided by 3 times 4, C2, which is also equal to 6 minus k, divided by 3 times 4 times minus k over 2 C0. So what I've done here is I express C2 in terms of C0 using this recurrence relation. And therefore what we note is that we can write it as 6 minus k times minus k over 3 times 4 times 2. Well, that's just 4 factorial. And similarly, I've written down the expressions for C3 and C5 in terms of C1. And because this recurrence relation relates the n terms that have the same parity, so the constants for n being odd are related to C1, and the constants for n being even are related to C0. We have two parts of the solution. We actually have two series solutions, and using the superposition principle, we can regroup these two series solutions into one general solution. And so I wrote down the first terms in our power series solution. And note that our first series solution, y1, is related to x to the power of even numbers, so when n is even. And y2 of x is an odd function, because n here is odd. So now that we have our series solution, let's see when these series actually converge to see the range of x for which this solution is valid. And in order to do that, we use the ratio test for each of these series. So first we test the convergence of y1. And so we compute the limit of the ratio of the two successive terms. So the limit as n tends towards infinity of tn plus 1 divided by tn, and the absolute value of this ratio. So we compute the ratio of the two successive terms. But notice that in the case of our first series, y1, the two successive terms are related by this recurrence relation over here. Indeed. For example, first we have C0 times 1, and then we have C2 times x squared. And so the ratio of the two successive terms is actually Cn plus 2 divided by Cn times x to the power of n plus 2 divided by x to the power of n. Of course, the absolute value of all that. And so x to the power of n plus 2 divided by x to the power of n, that's just x squared. And Cn plus 2 divided by Cn, well, we can use this recurrence relation to compute this ratio. And notice that the limit as n tends towards infinity of this ratio given by the recurrence relation is actually 1, because the highest degree term in the numerator is n squared, and the highest degree term in the denominator is also n squared. So the limit will tend towards 1. And therefore, the ratio will give out an answer of x squared. And so we know that the series converges when r is less than 1, which means when x belongs to the open interval containing -1 and 1. And this comes from the fact that x squared needs to be less than 1. And notice that the ratio test yields the same answer for y2. So this ratio test over here not only applies for y1, but also y2. Because the recurrence relation over here applies for both series solutions. And notice that for x is equal to -1 or 1, the ratio test does not yield a result because x squared will be equal to 1. And therefore we cannot determine whether these series solutions converge or not, since the ratio will be 1. In fact, we can use another convergence test, which is called Gauss's test, in order to prove that for x is equal to 1 or -1, these series diverge. But this is beyond the scope of this video. However, we can fine-tune k, the parameter k, in such a way that our solution y of x actually yields a series that converges, even for x being equal to -1 or 1. And so in such a case, how can we make y of x converge? And so in such a case, the way we can make our series solution converge is by getting rid of one part of the solution, so either y1 or y2, by setting the corresponding constant c0 or c1 equal to 0. And so for example, if I set c0 equals to 0, we will only get y2 as a solution. And then notice that y2 still diverges, and so we need to set k in such a way that y2 actually converges. So let me give an example. Let's say c0 is equal to 0, and therefore y1 of x, c1 times y1 of x is equal to 0. And then what we do, we can set k is equal to 2, and therefore y2 of x will be equal to, so x times 2 minus k, but k is equal to 2. So this will cancel out. And similarly, here we also have a 2 minus k times something else. So this cancels out. And so in general, the series actually stops, because the successive terms will always have a term of 2 minus k. But since k is equal to 2, 2 minus k will be equal to 0. And so the series stops after x. And so y2 of x will be equal to x. And actually, we can use the recurrence relation to find a general expression that k needs to have in order for a series to stop. Indeed, if we set k is equal to n times n plus 1, well, the successive terms after cn, so cn plus 2, cn plus 4, will be equal to 0. Indeed, if we set k is equal to n times n plus 1, we would have n times n plus 1 minus n times n plus 1, so 0. And so the terms after cn, cn plus 2, cn plus 4, will be 0, and the series hence stops. Usually in textbooks, we write k is equal to L times L plus 1, where L belongs to the natural set. And in the next video, I'll be going over more detail how we can fine-tune k to make y of x converge through what are known as the Legendre polynomials. So thank you for watching this video, and hope you liked it.